Alright, so this is our AP Chemistry lesson video for Chapter 10. This is Part 3, and I'm going to cover Section 10.6 and 10.7. Hopefully this one will not be as long as the previous one. Alright, so we're going to talk about gas mixtures, which of course will bring us to partial pressures. So Dalton's law of partial pressures states that the total pressure of a mixture of gases equals the sum of the pressures that each would exert if it were present alone. So our formula is PT, which is P total, equals the pressure of each of the individual gases. So of course you could have 2, you could have 3 or more. But we can also use this when we're using ideal gas law. So ideal gas law, PV equals nRT. If you rearrange it to solve for P, you get this. If you put in just one of the gases' amount of moles, you'll get the pressure for that one gas. But if you put your total amount of moles of gases, you'll get the total pressure. So you have to be careful of that when you're working with a mixture of gases. You got to know which pressure and which number of moles you're trying to use. So here, I know you probably can't see this. This gas is at 1 atm, this is at 1 atm, and this is at 1 atm. If we put all three gases together in a flask, it will be at 3 atm, because of course we just add them together. Alright, so in honors we used Dalton's law of partial pressures, but we didn't really apply it with anything else. We would just use that formula PT equals P1 plus P2 by itself. So now we're just going to apply it where maybe we need to use something like ideal gas law. So, sample exercise. It said a gaseous mixture made from 6 grams of O2 and 9 grams of CH4 is placed in a 15-liter vessel at 0 degrees Celsius. What is the partial pressure of each gas, and what is the total pressure in the vessel? Okay, so y'all, I can see that they gave me masses, so of course I can change grams to moles. So that means they gave me an N for oxygen, so I'm just going to call it N sub O2. I can change grams to moles here. So they gave me an N for CH4 or methane. And they gave me a volume, 15 liters, and they gave me a temperature, 0 degrees Celsius. And then we're looking for pressures. Well, we're looking for all the pressures. We want the pressure of the O2, the pressure of the CH4, and the total pressure. So I need 3 pressures. All right, so temperature, of course, I know I need to change to 273. And then let's go ahead and change these grams to moles. Okay, so I have 6 grams of O2. So we know 1 mole of O2 is 32 grams. So for that one, I got 0.1875 moles of O2. So see, that's what I can plug in as my N for oxygen. All right, and then I'm going to do this one. So I have 9 grams of CH4. We know 1 mole of CH4 equals the molar mass, which is 16 grams. And so once I solve that, I got 0.5625 moles of CH4. Alright, so now I'm ready to solve for these pressures. Okay, so we know PV equals nRT, but I'm solving for P. So I divide both sides by V. Alright, so I need the partial pressures. So first I'm just going to do oxygen. Okay, so I'm going to call this P sub O2. So that's my partial pressure for oxygen. So that means I need number of moles, but just of oxygen. Okay, so I'm going to put the 0.1875 moles in for this one. All right, R, let's see, what did they, oh, we're looking for pressure. I don't know which one I used. Okay, I used the atmospheres one. It doesn't matter. You can use the kilopascals one. Your answer would just be in kilopascals. So I did liters times ATM over moles times Kelvin. And then my temperature is 273 Kelvin. Then I divide the whole thing by the volume of 15 liters. So notice this is pressure of just oxygen because I only use the moles of oxygen. So my moles cancel, my liters cancel, my Kelvin cancels. I'm left with ATM. So my pressure for just oxygen that I got was 0.28 ATM. All right, and that was for O2 only. So that's my partial pressure for oxygen. But now I got to figure out my partial pressure for methane, or CH4. So again, I use the same formula, but this time I'm going to put in the moles of CH4, which is the 0.5625 moles. I'm going to keep my same R value, 0.0821 liters times ATM over moles times Kelvin. And I'm going to keep my same temperature, 273 Kelvin. And I keep my same volume, 15 liters. So the only thing that changed between these was moles. This is just moles of oxygen, this is just moles of CH4. So my moles cancel, my liters cancel, my Kelvin cancels, I'm left with ATM. And so for this one, I got 0.84 ATM, and that was just for CH4. okay? So it says, what is the partial pressure of each gas? That's what we just did, but it also says, what's the total pressure? Now, you could do this again. You could do another PV equals nRT, but in this case, plug in the total number of moles, add those together, and then solve. But y'all, I already have the two partial pressures, so let's just use Dalton's law. Total is your partials added together. So when I do 0.28 plus 0.84, I end up getting a total of 1.12. So my P total equals that. And so all I did to get that was I added these two together. Okay, but again, you could have redone this by plugging in the total number of moles and you would get the same answer. All right, so like I said, we're just taking Dalton's law and we're using it as a step in a problem instead of it being the only step. So that's the difference in what we do in honors versus AP. All right, so let's move on. So you try the next one, and I'll assume you've done that, and it's similar to the one I just showed you, so now we'll look at it together. So for yours, you only had to do total pressure. So in this case, I wouldn't even have to do those two separate steps. I would just do total together. So it says, what is the total pressure? So I'm looking for P total. Exerted by a mixture of 2 grams of hydrogen and 8 grams of nitrogen. So I'm going to have to go grams to moles for both of these. And then together, I can plug those in as N. Okay, because see, I need the total pressure. That means I want the total number of moles. At 273 Kelvin, so you didn't even have to change your temperature, and 10 liters. So that's my volume. All right, so we know PV equals nRT. We're solving for P, so I divide both sides by V. In this case, because I'm looking for P total, I want my total moles of gas times RT over V. All right, so y'all, I can't just combine these and start with 10 grams. Each of them has its own molar mass, so I have to do them separately. Okay, so I start with 2 grams of H2. All right, 1 mole of H2 is, of course, 2 grams. So that one's pretty easy. So that's 1 mole of H2. And then I have 8 grams of N2. And 1 mole of N2, of course, equals molar mass, which is 28 grams of N2. And sorry, I'm doing this part kind of fast because I think we know how to go from grams to moles at this point. All right, so, and I got 0.29 moles of N2. So see, in the last problem, because I needed partial pressures, I did just the moles of this in the formula, just the moles of this in the formula. But we want the total pressure, so I just need to add my two amounts of moles together. So I have 1.29 moles total. Okay, so that's what I'll plug in for N. And you only have to do this once because you only were asked for total pressure. All right, so then I just plug in. So my N is 1.29 moles. My R is, did I use, okay, seems like I'm favoring the 0.0821 while I'm doing all these, which is fine. Again, it doesn't matter which one you do. It doesn't specify what unit it wants pressure in, times temperature, which is 273 Kelvin, over the volume, which is 10 liters. So my moles cancel, my Kelvin cancel, my liters cancel, I'm left with ATM, and I ended up getting 2.89 ATM. And so again, this is my total pressure because I added up the two amounts of moles. If I had just plugged in 1 mole, I would have gotten the pressure of just hydrogen. If I had just plugged in 0.29, I would have gotten just the pressure for nitrogen. But it asked me for total, so I just had to add those moles together. So hopefully you got that one right. Alright, so next we're going to learn something new. I usually don't have time to cover this in honors, so most likely you haven't seen mole fraction before. So mole fraction, which is represented by S, is a dimensionless number, so no units, that expresses the ratio of the number of moles of one component to the total number of moles in a mixture. So it's N1, so that's of whichever component you're talking about, over N total. It's kind of like a percentage, but we don't multiply it by 100. So it's just the decimal version of that. All right, so it's N1 over NT total. That gives us our mole fraction. And so if you have the total pressure and you know the mole fraction of a gas, if you multiply them, that'll give you the pressure of just that gas. So as long as you know mole fraction, you can figure out the partial pressure of that gas. All right, so let's look at one together. So it says, a study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.5 mole % CO2, 18 mole % O2, and 80.5 mole percent argon. Calculate the partial pressure of O2 in the mixture if the total pressure of the atmosphere is to be 745 torr. Okay, so y'all, we know the total pressure here. Okay, and we know we can get pressure of just oxygen if we do the mole fraction of just oxygen times the total pressure. Okay, so see, we have the total pressure, we just need that mole fraction for oxygen. All right, so on this one, these are in percentages. Okay, so see, 1.5 mole percent, 18 mole percent, 80.5 mole percent. So these are percentages, so remember, we don't want it in percent form. So the way you take it out of percent form is, of course, move the decimal 2 places, or, of course, divide by 100. Okay, so once I did that, we're only worried about oxygen, so I can move it over 2 places. So that means its mole fraction is just 0.18. So once I know that, I can just say, okay, well, my pressure of oxygen is 0.18 times my total pressure, which is 745 torr. So once I multiply that, I got 134.1 torr. Okay, so y'all, what you have to be careful of is if they give you the percent, you need to get it out of percent form. You want it in decimal form. Because otherwise, if I multiply 18 by 745, I'm going to get something bigger than 745. Remember, y'all, we're trying to get just a partial pressure, so your answer must be less than that. Otherwise, it doesn't make any sense. All right, so I see this is part A, so it looks like there's probably going to be another part. So if I need this number on the next slide, I'll just rewrite it for us. All right, it says, if this atmosphere is to be held in a 121 liter space, all right, so I got a volume, at 295 Kelvin, so I got a temperature, then how many moles of oxygen are needed? So I'm looking for N. So right now we're technically missing P, but we know that P was 134.1 torr. Okay, and we got that from part A. All right, so we know that clearly this is looking like a PV equals nRT problem. We're solving for moles of oxygen. So I solve for N, so I divide both sides by RT. So N equals my pressure. Well, the problem is I can't use that pressure. I have to have kPa or ATM. I most likely changed to ATM. I did. So I put 760 torr on bottom, 1 ATM on top, and easily you could have gone to kPa instead. And I got 0.176 ATM. All right, so that's my pressure. So I did 0.176 ATM times my volume, which is 121 liters, over my R value. Since I used ATM, I used 0.0821 liters times ATM over moles times Kelvin, times my temperature, which is 295 Kelvin. So my ATM, liters, Kelvin cancel. I'm left with moles, which is what it asked me for. And so once I solved, I got 0.88 moles of O2. Just like that. All right? So like I said, what we're doing at this point is we're just working with multiple different gas laws and kind of doing a multi-step problem with them. So see, it might start out with mole fraction or Dalton's law, but then it might go into ideal gas law. It's just, you never know. They're all connected. All right, so you try this one. Notice before you try it that these are mole percent. So make sure you divide by 100 or move that decimal 2 places to get the mole fraction. All right, so I'll assume you've paused it and tried it. Let's look at it together. So it says, from the data gathered by Voyager 1, scientists have estimated that the composition of the atmosphere of Titan, estimated the composition of the atmosphere of Titan. The total pressure on the surface of Titan is 1220 torr, so there's my total. The atmosphere consists of 82% N2, 12 mole percent argon, and 6 mole percent CH4. Calculate the partial pressures of each of the gases in Titan's atmosphere. Okay, so remember, the pressure of one gas is the mole fraction of that gas times the total pressure. Okay, I have my total pressure. I have the mole percent of each one. So I just need to move that decimal over to get it to a mole fraction. So this would be 0.82 for nitrogen. It would be 0.12 for argon, and it would be 0.06 for CH4. So remember, you have to divide by 100 or move it 2 places. Don't just put it at the front. And so then I just do this for each gas. All right, so I'm just going to start with my nitrogen. So my pressure of nitrogen is my mole fraction, which is 0.82, times my total pressure, which is 1220 torr. And so for this one, I got, let's see, where's nitrogen? 1000.4 torr. Okay, so that's my pressure for just nitrogen. All right, next I'll go to argon. So my pressure for argon is my mole fraction for argon, which is 0.12, times my total pressure, 1220 torr. So for argon, I ended up getting 146.4 torr, just like that. All right, and then last one is my pressure of CH4. So I do my, my mole fraction of CH4, which is 0.06, times my 1220 torr, which is my total pressure. And so for this one, I got 73.2 torr. And so those are my three partial pressures. So the important thing to remember is if they give you mole percent, make sure you change it to mole fraction, which means you divide by 100. You don't want a percentage, you want a decimal. All right, so hopefully you got that one right. All right, so next thing we're going to talk about, this deals with Dalton's law of partial pressures, and that is when you collect a gas over water. So sometimes gases are collected in a lab by water displacement. However, some of the gas would be water vapor, so that must be subtracted to get an accurate pressure. So sometimes what they'll do is they'll fill an entire container with water. They'll have a reaction that's producing a gas, and it'll have a little tube that goes into that container. So as bubbles come up, the level of the water goes down because now there's a gas there. But the problem is some of this water is then going to evaporate. So up here we don't just have O2 gas, we also have water vapor. And so if you're trying to figure out the pressure of just the O2 gas, you're going to have to subtract the water vapor or you're going to have too high a number. So our total pressure is just the pressure of each added together. So it's the gas plus the water. This is the same as P1 plus P2. Okay, same formula, we're just applying it to when you collect a gas over water. So let's look at the first one together. So it says, a sample of KClO3 is decomposed, producing O2 gas that's collected over water. The volume of the gas collected is 0.25 liters, so there's a volume. At 26 degrees Celsius, there's a temperature, and 765 torr, there's a pressure. And that's my total pressure, so let me call it PT. The pressure for just water at 26 degrees is 25 torr. Okay, so there's my pressure for just water. So then it says, how many moles of O2 are collected? All right, so y'all, that means I'm going to be doing a partial pressure problem to get the pressure of just the gas, and then to get moles, I'm going to have to do ideal gas law. All right, so we know that our P of our gas, or our oxygen, we'll go ahead and call it oxygen since we know what it is the total pressure minus the pressure of just the water. Okay, so my total pressure is 765 torr. The pressure of water at that temperature is 25 torr. So once I subtract that, I ended up getting 740 torr. So once I have my pressure, so this is my pressure now of just the O2. So if I'm trying to figure out moles of O2, now I need to use PV equals nRT. All right, so I have PV equals nRT, but I'm solving for N, so I divide both sides by R and T. So N equals pressure. Well, I can't use torr for ideal gas law, so I need to change it to ATM or kilopascals. So 760 torr. Ooh, sorry, that's super sloppy. Just listen to what I say. Don't look at my handwriting. I'm left-handed. You know, we're lucky we can even write it all. All right, so that equals 1 ATM. So my torr cancels. And so I ended up getting 0.97 ATM. So that's the pressure I can plug in. So 0.97 ATM times my volume, which they gave me right here, 0.25 liters, over my R value. Well, since I used ATM, I'm going to use 0.0821 liters times ATM over moles times Kelvin, and then times my temperature. So we got to change that. 26 degrees Celsius, I got to add 273, and so I ended up getting 299 Kelvin. So I'll put my 299 Kelvin right there. Okay, so ATM, liters, Kelvin cancels. I'm left with moles, which is perfect. That's what it asked me for. So once I solved, I got, let's see, there we are, 0.0099 moles of O2. Whew, that's not very many moles of O2. But hey, they collected something. All right. Then it says how many of KClO3 are decomposed. So this is where then I would need to do a stoichiometry question, because whenever you go from one substance to another, you're going to have to do stoichiometry. So we need to write our reaction first, because notice they didn't tell me the reaction here. All right, so we know we have KClO3, and we know it's decomposing. We know we're getting oxygen, so in other words, the oxygen is separating. So we're going to have KCl and O2. Okay, so it's just decomposition. So I need to balance to make sure I can do my mole ratio. So I have 1K, 1K, 1Cl, 1Cl, 3 O's and 2 O's, so I just need a 3 and a 2. All right, so I know I have 0.0099 moles of O2. So my first step is mole ratio. So 3 moles of oxygen, 3 moles O2, requires 2 moles of KClO3. But notice it asked me for grams, so I can't stop at moles, so I go one more step. So I put my 1 mole of KClO3 on bottom, and then I put molar mass on top. So I just add up KClO3, and so for that I got about 122.5 grams of KClO3. And so I just multiply and divide. So I got 0.8085 grams of KClO3. Okay, so y'all, one thing that I would point out is a lot of times you've got to kind of combine ideal gas law with stoichiometry, or ideal gas law with Dalton's law, or something like that. Okay, so just be prepared to have to combine knowledge from different units. Okay, the AP exam is not going to just ask you about one thing at a time. Okay, a lot of times they start kind of meshing everything together. Because remember, it's all related. Like, that's the thing. The sooner you realize all of it is related, and don't compartmentalize it into, oh, well, that was unit 2, or this was, it's all the same thing. It's just building as we go. All right, so y'all try this one. So you have a similar one. You got the reaction, though, so you're welcome. All right, so y'all try this one. I'll assume you've done that, and let's look at it together. So it says, when a sample of NH4NO2 is decomposed in a test tube, 511 milliliters of N2 gas is collected over water. Okay, so I have a volume at 26 degrees Celsius, so I have a temperature, and 745 torr, so I have a pressure, total pressure, that's my total. How many grams of NH4NO2 were decomposed? Pressure for water is 25 torr. Okay, so the first thing I need to do is get the pressure of just the gas. I can't use PV equals nRT if I don't have the pressure of just the gas. All right, so we have PV equals nRT. We're trying to solve for moles of N2. Okay, that's what I'm looking for first. Because remember, if I'm going to do a stoichiometry problem, I need to know moles or grams of something. All right, so first I got to figure out my pressure. So here's the total pressure, here's the pressure of just water. Okay, so to get the pressure of just the gas, I'm going to do the total pressure, 745 torr minus just the partial pressure of water, which is 25 torr. So of course, I'm going to get 720 torr, but I'm about to use ideal gas law, so I'm going to go ahead and convert that. So 760 torr is 1 ATM, so my torr cancel, and I end up getting 0.95 ATM. So that is my pressure. Alright, so now I have pressure, I have volume. Of course, I'm going to need to change this to liters, so just divide by 1,000, so it'll be that. I have temperature, so let me add 273 to that, and then it becomes 299 Kelvin. So now I'm ready to plug in. Okay, so my pressure is 0.95 ATM. My volume is 0.511 liters. My R value is 0.0821 liters times ATM over moles times Kelvin. And my temperature is 299 Kelvin. So my ATM, my Kelvin, my liters cancel, I'm left with moles. And so once I solved, I got 0.0198 moles of N2. So notice I know I'm talking about moles of N2 because it says we were collecting N2 gas. So that's one of the things you got to be careful of, is a lot of you will assume, oh, well, I got moles of this, so now I can just go to grams of this. Well, remember, it didn't tell me anything about that yet, all right? But it did ask me about it. So how many grams of NH4NO2 were decomposed? So now I can do a stoichiometry problem. So I can grab my 1 mole of N2 requires 1 mole of NH4NO2, but then we got to get to grams. So I can say, okay, well, 1 mole of NH4NO2 is, and then I just add up molar mass for NH4NO2, I got 64 grams. And so my moles cancel, so then I just multiply. And so I got 1.27 grams of NH4NO2. Just like that. So again, we used a Dalton's law of partial pressures to subtract and figure out just the pressure of N2. Then we use PV equals nRT to get to moles of N2. Then we use stoichiometry to get to grams of NH4NO2. So see, if you're like me, I love this type of problem because you have to kind of think your way through it. But I know many of you are like, oh my gosh, it's so many steps. But don't worry, y'all. The better you get at them, the less scary they are. And so hopefully you got that one right. All right, so 10.7. So kinetic molecular theory. The kinetic molecular theory is summarized by the following statements. Gases consist of large numbers of particles that are in constant random motion. So in honors, we would have said this is constant motion. The volume of the gas particles is negligible compared to the total volume in which the gases contain. So in honors, we would have said the particles have no volume. Remember, they do have a volume, it's just insignificant compared. Attractive and repulsive forces between the gas molecules are negligible. So in honors, we would have said no forces. Again, they're not actually zero, but they're just very small. And then collisions between particles are perfectly elastic, which means energy is conserved. And so we would have said perfectly elastic collisions. And then the average kinetic energy of the gas particles is directly proportional to absolute Kelvin temperature. So we would have said kinetic energy and Kelvin temperature are directly proportional. So the pressure of a gas is caused by the collisions of particles with the wall of the container. The magnitude of the pressure is determined both by how often and how forcefully the molecules strike the walls. So if we can make them collide more often or in a harder way, like with more force, those will both increase pressure. So the absolute or Kelvin temperature of a gas is the measure of the average kinetic energy of its particles. Two different gases at the same temperature have the same average kinetic energy, regardless of the molar masses or identities of the gas. Okay, so two different temperatures, same average kinetic energy. Because temperature is just a measure of average kinetic energy. Although the particles in a sample of gas have an average kinetic energy and hence an average speed, the individual particles move at varying speeds. So think of it like when you take a test in class. There's a class average, but some people made higher than that, some people made lower. So the RMS, or root mean square speed, is represented by a U, and it is the speed of a molecule possessing average kinetic energy. So the RMS speed is not quite the same as average speed, but the difference between the two is very small. As temperature increases, RMS speed increases, which makes sense because as temperature increases, average kinetic energy increases. But one thing I do want to point out is as temperature increases though, notice how the shape of the line increases. It's not like 0 is here and then the 500 is the same shape. As it heats up, you'll notice that the peak broadens out. Okay, it's not as sharp of a peak. So that means there's a larger range of speeds happening as you get hotter. So let's look at the first sample exercise together. So it says, a sample of O2 is initially at STP, and it's compressed to a smaller volume at constant temperature. What does this change what effect does this change have on the average kinetic energy of the O2 molecules, the average speed of the O2 molecules, and is there a part C? Oh, there's a part C and D, so I'll have to click to see those. All right, so y'all, we have O2 gas. We are making a smaller volume at constant temperature. So remember, this is like what I showed you in one of the other videos. Like we have a piston. Okay, so we have a piston. We got some gas particles. What we're doing is we are lowering the piston, which squeezes the gas particles together. Okay, so we lowered the piston and squeezed the particles closer. Notice it says at constant temperature. That's important. So part A, it says what effect does it have on the average kinetic energy? Well, average kinetic energy is the measure of temperature. So what happened to temperature is constant. So there's no effect. The average kinetic energy is going to remain the same. Next, it says the average speed of the O2 molecules. Well, again, we didn't change temperature. Temperature is what affects the speed of the molecules, so there's no effect on that either because it's the same temperature. Okay, so sometimes that's what you got to look for is little key words that you might think are not important are incredibly important. Okay, so let's look at part C and D. All right, so it says the total number of, whoops. All right, there we go. It says the total number of collisions of O2 molecules with the containers in walls in a unit time. Okay, well remember they used to have this much room to move around. Now they only have this much. So the collisions are going to increase because we have a smaller volume. Then it says the number of collisions of O2 molecules with a unit area of container wall per unit time. Well again, we have a smaller volume at this point, so the number of collisions is going to increase. Don't let the wordiness of these two throw you off. Okay, if temperature doesn't change, speed or kinetic energy doesn't change, then in this case, volume changed, so it is going to increase the number of collisions because the volume got smaller. Alright, so y'all tried this one. I'll assume you paused it and tried it, and we'll look at it together. So it says, how is the RMS speed of N2 molecules in a gas sample changed by an increase in temperature? Temperature does change the speed, so if I increase temperature, speed will increase. Alright, the next one says an increase in volume. Volume gives them more room to spread out, and there will be less collisions and lower pressure, but it didn't ask me about that. It asked me about speed. If I just increase the volume, speed stays the same. So there's no effect. No effect. Alright, next is mixing with a sample of argon at the same temperature. So remember, speed is affected, or kinetic energy is affected by temperature. So if you just add more argon, sure there's going to be more collisions and more pressure, but the speed itself is not going to change. There will be no effect. Alright, so hopefully you got that right. You could have put the same for part B and C. That probably made more sense than me writing none. They do have a speed, it just doesn't change. I meant like the effect of it would be none. I just realized that was probably kind of confusing. Alright, so that is our third video, and so hopefully, like I said, there was a few new things for honors, but really, if you were in honors, we just started kind of adding things together, like combining ideal gas law with stoichiometry, or combining ideal gas law with Dalton's law of partial pressures. But the only new thing we really learned is that mole fraction.